So our final speaker today is Nick Heaton from Cadence. He's going to talk about stress testing coherent systems. He's a distinguished engineer at Cadence with a long-time Cadence Verification RnD Leader who has worked in SoC Verification for more than 20 years. He is currently the Architect and RnD Leader for Cadence's SoC Verification products. So over to you. Thanks, Nick.
Hi, everybody. Thanks to Dave and Alex for giving their presentations, which I think somewhat sets the scene. It is a complex topic, so I'm going to zoom in on one specific thing here. We've been working on coherent systems for a while, so I'm going to go and talk about traffic libraries and specifically enhancements we've made, significant enhancements we've made as we've worked with some of our leading customers. So System VIP, we launched that in 2020, but we've been working on coherency stress testing for some time. But in the last sort of 2 years, we've been pushing the boundaries with customers doing ARMv9 systems, which have a whole raft of further capabilities that further complicate the coherency challenge. And we have a number of libraries which really, through our Perspex tool, these are portable stimulus, and you can target them to coreless or core-based simulation or acceleration environments. So, you know, you need to start this process early if possible, but portable stimulus allows you to evolve it through all the way to potentially post-silicon as well. So I'm going to go through a couple of slides quite quickly. So these are our libraries. We're going to focus on the coherency library and specifically stress scenarios. We've had coherency library for 4 years or more, and so in the last year we've added a considerable amount of new content as the requirements have become, you know, clear on the bleeding edge, particularly of ARMv9, and but we support RISC-V as well. But the libraries cover other things that can also play in this space. Performance plays in this space as well, as does PCIe as a coherent I/O device and CXL. So there's going to be further extensions to this content with chiplet to chiplet SMP kind of systems that are becoming more common now. So what are we trying to do here? Obviously, we're trying to uncover more bugs pre-silicon, ideally, reach corner cases, get higher coverage. And the benefit of having a stress library is that all of the aggregated experience of the years we've spent and with multiple product engineers and application engineers working in different accounts is that all of that gets rolled back and the scenarios expand. We have more mature content for more analysis, and it keeps evolving. This is not a topic we're done with. We're continually working and investing in this space. We have a team, a significant team, working on just on library content. So the key kind of factors and dimensions of when we talk about stress are the timing density. So whenever you generate scenarios, when it's stimulus, if you like, coherent stress stimulus has to have some kind of scheduling overhead. So obviously you try and minimize that overhead. You want the most dense content you can get in terms of different assembly language opcodes. There are a lot of permutations. This is particularly true for embedded core testing. But you know, we can drive this traffic through a VIP or drive it through a core. There are certain things you can't do through a VIP that you have to do with a core, and vice versa. So you need both, support for both, and obviously we work with our Cadence VIP team to ensure that we support all the various protocols as we move both for simulation and acceleration. Embedding variants in the runtime. So this isn't like writing device drivers. This is very much like creating a VIP, hence we call it system VIP. You need to create content that has dimensions of randomization in order that you can create the conditions under which bugs will be uncovered. And that's particularly true for resourcing. The way that cache lines are shared across multiple caches, memories, particularly if you're using Amber Chai interconnects that have home nodes and subordinate nodes. So HNF, SNF quite often are hashed. What do we mean by that? Well, in order to improve the performance given a range of workloads, a lot of server class devices will hash the addressing of their memory controllers and their home nodes, which are where the distributed cache lives in the interconnect. They will hash the addresses to kind of randomly distribute the workloads across those. That makes it kind of difficult because to stress the system, because those mechanisms are implicitly designed to try and reduce the stress. So in order to actually stress hashed systems, you need to be able to generate hash defeating sequences of addresses so that the same you can ensure you constantly hit a single DDR controller or constantly hit a single cache. And that way stress it. In other words, push its buffers to the limits, push its command ordering to the limits. You need to be able to support virtual memory as well, because obviously virtual memory is a part and parcel of the way the address maps are configured in these systems, and therefore your coherent I/O devices will probably have a system MMU in them and therefore be virtualized, and you need those coherent I/O devices to play with the processor cores that you're also driving, again, to create stress. In most systems, you would buy your processor clusters all from they'll all be the same provider. Maybe the interconnects from the same provider. So you might think, well, aren't these systems fully verified, so I don't need to do this? Well, it's very rare you can find a provider who also has PCIe, system MMU, DDR controllers, UCIe. There are always a mix of suppliers, and your design will almost certainly be a unique combination of those, and this is why this is a problem you need to care about. There are also, you want to inject kind of noise. Sometimes people call these irritators. So you may have a certain set of cache partners operating a cache scenario, but it may be useful to push the memory controller or push the caches from other sources that maybe aren't related to those tests, but can irritate the test and introduce potential noise, and sometimes that can uncover bugs. And you also, you need to target specific features in your system, and these may be specific to your system. So it's important that you can mix and match library content with some specific things that may be unique to your system. So we're going to deep dive into a couple of these topics. So runtime variants, we have content where you can actually, this is portable stimulus at the top and showing you the C code that comes out as a result. Perspec is a constraint solver, so you write content in portable stimulus to build a scenario, and then you have a constraint solver will give you a solution for that scenario, and ultimately then generate C code from it. This allows you to do things like generate random scenarios up front and look at the coverage of that before you even run it. And that can become particularly important when you're running on real embedded CPUs, say in simulation, because the simulation time can be significant. So you ideally want to know you're firstly running the best tests that you can get before you run it, and then run it obviously on whichever platform you're targeted to. But you can also therefore analyze, longer scenarios, more iterations, and create stress. Resource stressing as well. So I talked about HNF, so home nodes, which are where in a CHI or CHI interconnect, you will have home nodes which are one or more distributed cache elements that you may want to target specifically. Each of those caches will have transaction buffers, they'll have cache sizes that you maybe want to stress. So you may say, right, I want to target a particular HNF and I want to reduce the allocation and thereby more readily get specific stress hitting that particular HNF. And the same with TLBs. So TLBs are really, the virtual memory unit of cache. Translation look-aside buffers are really cached page tables in your virtual memory system. So they have a similar kind of characteristic, and you may want to control allocation of virtual memory IDs in order to stress your system. We talked about noise again, and we have content in the library specifically to allow you to target noise, whether it's allocating noise in the same address when you generate the test, or noise at runtime, so you can control when the noise is injected. And this is a quick snapshot of what we call our gallery. So the way Perspec works is you get a gallery of content in a GUI called a composer, and you can drag and drop these actions or whole scenarios. So you see in the top right, we've got whole scenarios, false sharing, true sharing, or you can have concurrently with those, you can inject noise. You control with the composer how you assemble a scenario concurrently, sequentially, and then you solve it and generate an actual concrete C test. So there's nothing stopping you mix and matching these actions with your own actions that you can assemble yourself, write your own content, mix and match, and get unique scenarios that will stress your system in the way that you need to stress your system. So I wanted to leave some time for questions. So we've invested an awful lot of time in building massive extensions to our coherency library to add stress to it, and you've seen a number of ways in which the stress is potentially added. Lots of runtime address and data variations, stressing the processors, the cache lines, the mesh nodes. You need to decide what your target is for the stress. Is it the CPUs clusters on their own? Is it the interconnects? Is it the DDR? Is it the whole thing? And typically our customers take a bottom-up approach to this, where they'll look at stressing maybe the interconnect with the DDR. And this is particularly needed when you have things like MPAM. So there's a memory partitioning and allocation and management architectural expansion in ARMv9, which specifically allows you to allocate bandwidth and cache to a particular cluster of partition IDs, and those partition IDs are software allocated. So you need to be able to do some of that testing at a VIP simulation level, because you cannot see the throttling mechanism once the embedded cores are included, because it's inside the embedded core. So you can test the throttling mechanism with verification IP in simulation, then add your embedded cores and run the same tests and validate using performance monitoring units in the IP to check that you've got the right cache allocation, the right bandwidth allocation. So there's lots of complexity here. There's a whole spectrum of use models that you need to be able to support, and the libraries work hand in hand with all of those use models across Cadence tools. So hopefully that gives time for one or two questions. Obviously, very happy to give a lot more detail as both presenters have highlighted. This is a complicated topic, and it requires tools at all the different levels in order to comprehensively cover the picture. So reach out to myself or your local Cadence AE if you'd like to follow up on any of these topics.
Okay, thanks, Nick. We have a couple of short questions. You talked about performance verification. Is there any sort of infrastructure which allows you to know that you've got the right, most efficient cache design, or you've architected cache?
Yeah, so that's a highly complex question. One of the things we do is, so we use the traffic libraries that I've described here. We have performance libraries as well. Specifically, we can deliver prescribed cache hit miss ratios in the traffic so that you can explore whether your system achieves, with a certain cache hit miss ratio, whether it can achieve a certain bandwidth. So you have very easily the ability to set, I want this many gigabytes, I want this mix of read writes, these kind of address patterns, and this kind of cache hit miss ratio, and then go and you need another tool, performance analysis tool that we provide, which will tell you whether you've hit the right bandwidth. If there are issues, you can then use that to also debug where the issues are. So yeah, whether cache is most optimal is a tricky one. Certainly from a DDR point of view, you also want to know that you've hit an expected DDR efficiency. Again, most systems it's almost impossible to get 100% DDR efficiency unless you've got very contrived tests. But with a range of workloads, you want to get to 70 to 80% DDR efficiency. Again, you need the combination of traffic and tools to make sure that's in the right ballpark.
Perfect. Okay, thanks. We've got another couple of questions which we'll share on email, but I think we've run out, and we'd like to finish at one. So thank you very much. Next presentation will be put online as well as the recording as well. Thanks, Nick. Thank you.
Okay, pleasure. Thank you.
Do you want to share my screen, please? Okay. Thank you. Can you see that?
Yes, it's a full screen.
Okay. So thank you for participating in the DV Club today, where we focused on cache coherency verification. And thank you to our speakers today, Dave, Alex, and Nick. Thank you to our sponsors who make this possible: Agnestis, Cadence, Synopsys, Sprecher, Impress, ARM, and STR, venue sponsors, and Textual is the organizer. The presentations will be put on. You'll probably get the PDF today, and the recordings within a week. They'll be there, so you can go and look at them again or share them with your friends. Remember to send your suggestions to me. We do actually go through those suggestions, and we create DV clubs on the back of them. Some of the things which are coming up: on the 17th of October, we have AI ML verification. And then 28th of November, we have auto generation of verification infrastructure for IP to SoC level verification. And one missing here is our Verification Futures Conference, which is next week in Austin. You probably will receive an email about that, and you can either physically attend if you're based in Austin or based in the US. Otherwise, you can attend virtually, and we I think already have about over 800 registrations for that. Okay, thank you very much. Thank you.
Thank you, everyone.